Okay. Hello everyone, welcome to this edition of ICTS String Seminar. I hope that everyone is doing fine and everyone is healthy. So today we have the pleasure of having Professor Seok Kim from Seoul National University, and he's going to tell us about black hole microstate and the index. So over to you, Professor Kim.
Okay, thank you very much. First of all, thank you so much for inviting me to give a talk. It's great to see old faces and new faces and familiar names. It's a great pleasure to get this chance to talk about some of my recent thoughts. So, I tried my best to make the content simple. It's about some black hole thermodynamics in antidistant spacetime and trying to better understand it. The BPS black hole thermodynamics in AdS CFT using some Witten index. It's a very technical subject, but I'm trying to talk about least technical side of it today. Okay, so so broadly speaking, what I'm going to talk to you is a very simple fact. I present a very simple fact about Witten indices in general. Witten indices when the corresponding charges and degeneracies become macroscopic, so that one can use it to study black holes. And it's really about simple fact, which I belatedly realized very recently while I was trying to study microscopics of antidistant black holes. The simple story is about the -1 sign, which very often which appears everywhere in the index-like partition functions. This -1 is making possible all the magical structures of the Witten index. So it's kind of art of playing with -1. But if one is a bit careless about physics, this -1 can also easily obscure the physics. So I'm going to tell you how to extract out the proper macroscopic physics out of these partition functions. So the importance of Witten index in the context of black holes cannot be really over exaggerated. So over the many decades, there have been general attempts and long endeavors to better statistically understand the black hole thermodynamics in various settings, asymptotically flat, asymptotically AdS, various things. And in order to study these kind of questions, the microscopic statistical grounds of this black hole thermodynamic behavior, one should really set up the quantum mechanical problem, the microscopic quantum mechanical problem, for the system describing the matters which are lurking inside the black holes. Okay? And in order for the corresponding classical solution of black holes to be reliable, so that all these geometric realization of thermodynamic behaviors can be trusted in that regime, somehow it always turns out that in this regime where classical solutions are reliable, the corresponding microscopic quantum system always turns out to be strongly coupled. So one have to count the microstates and do thermodynamics at strong coupling. So it's very difficult. So one way of doing some rigorous study has long been focusing on certain BPS sectors of superstring theory from early mid-90s, and then study a suitably defined Witten index partition functions, which are computable rigorously at strong coupling very often. So the role of Witten index in doing some quantitative black hole thermodynamics is very significant. So I'm going to show to you a kind of typical behavior about the signs appearing in the index when this index becomes macroscopic. And this plays some roles to extract the correct physics of the BPS black holes in the context of AdS CFT. So let me start by saying a few general statements about Witten indices. It can be defined, well, I just used the term Witten index very broadly. Some people use very long terminologies for QFT indices like Superconformal index, twisted index, various indices. To me, everything is Witten index. Okay? So this index version of partition function can be defined both for quantum mechanics and quantum field theory if they are preserving some supersymmetries. They may count either ground states of the system, or they may count some BPS excited states, depending on how you define the index. And of course, it counts the degrees of freedom in the Hilbert space with -1 to the fermion number factor, so that every fermionic state is counted with minus sign. You subtract the degree of freedom rather than adding it. Okay? So the magic of this Witten index with this -1 factors included is that it's a sort of supersymmetry preserving variable. And due to the help of this supersymmetry, roughly the kind of non-normalization behaviors, it often turns out that strong coupling calculus of the spectrum as an index is doable. Okay? Especially if there are charges in this system, in this sector of BPS sector, commuting with the supersymmetry in question, one can also introduce chemical potentials in Witten indices, making it really look like thermal partition functions with temperature and chemical potentials for particle numbers and so on. So if one can introduce this fugacity in the index, this index, like normal thermal partition function, admits a fugacity expansion, which is the analog of the low temperature expansion of the thermal partition function. Schematically, I call X the fugacity. There may be multiple of them. And schematically, I call J, which are charges commuting with supersymmetry. And it's traced over the Hilbert space. And the schematic definition of the index is given as follows. You expand in fugacity, like low temperature expansion. The coefficient, which are function of the charges, will be integers, counting the suitable states with minus signs. Okay? So these are integers, and they can be positive or negative, depending on whether there are more bosons or more fermions in this sector. To use this object to study black holes, the characteristic property of semi-classical black hole is that they have macroscopic charges. When they are macroscopic charges, we want to understand the approximate method, which extracts out this coefficient, whose log is giving you the entropy of black hole. So the contour integral, which extracts out this integer coefficient out of this function, is given as follows. Okay? It's taking the form of inverse Laplace transformation. And what we want to do is at large charge, which I schematically denote by J, we want to do a saddle point approximation of integral. And the saddle point value will give rise to a certain function of J, which can be interpreted as exponential of the macroscopic entropy of the index. Okay? So this saddle point approximation we call Legendre transformation. But now we take into account the fact that this is an index. This can be positive number or this can be negative number as you change this, this quantized value of charges. So changing J's by its quantum, gradually increasing it, the sign factor in front of these omegas can oscillate. So if you do the calculation carefully, at some sector you should give positive number, at some sector you should give negative number, sometimes they should oscillate, and the Legendre transformation should be doing that business if you're doing the calculation correctly. This is the typical behavior we should, so-called typical behavior we should expect to be in there. It can be either positive or negative. So if you, as a function of J, the number can oscillate between positive and negative number with certain wavelength or so on. That's the typical thing you should expect. Of course, there are exceptional cases where all coefficients are positive for certain magical reasons, like what's called a K3 elliptic genus. We know of some examples like that, but it seems fair to say that the typical behavior is not like that. There might positive and negative signs oscillating around. And this sign oscillation of a macroscopic index can be treated in quite a standard manner in this saddle point approximation. This is a very elementary textbook exercise. So I'm going to start by reviewing this with a very, very simple toy example before getting into more complicated quantum field theory partition functions. So the contents are the following. Okay, I'm basically going to do kind of thermodynamics in the Witten index version. So you can have two viewpoints. You can have a viewpoint. You can view this problem of extracting out the degeneracy information from the viewpoint of microcanonical ensemble, and you can do a similar study from the viewpoint of a grand canonical ensemble. And these two viewpoints are related, but depending on which viewpoint you choose, the relevant physics that you can do are sometimes slightly different. Okay? So firstly, in the microcanonical viewpoint, I try to explain to you how to extract out the correct degeneracies of the index, including the sign factor, using the Legendre transformation. It's a mathematical physics exercise. So to be extremely simple, I'll start with a toy model in which you can compute everything explicitly. So getting some lessons with and pictures with toy models, we're going to move on to the conformal field theory indices and related AdS black holes. Okay. There are many literatures. Old one, reasonably recent one, very recent one, and there are actually many, many more. But today's story of mine would be very simple, so I've omitted many, many things actually, including my ones, papers, and so on. But I mentioned some of them during the talk. And then the goal is to properly understand, one goal is to properly understand the microscopic entropy of black holes, which have been pioneered by many people. And I also see that many people in the audiences have been contributed a lot on this subject in the past 2 years. Then I move on to the similar question of the index, macroscopic index, from the grand canonical ensemble point of view, in which one can study a very interesting phenomenon of the so-called Hawking page transition from the index. So this is a transition in which a two saddle point of thermal graviton and black holes in antidistant space are competing with each other. And as you gradually increase the temperature, at a certain point, there appears a first order phase transition, after which some large AdS black holes are thermodynamically nucleated. So this can be studied to a certain extent using this index, having in mind all the subtleties I'll tell you. So yeah, after which I try to briefly conclude. So let me really start by simply toy model. Toy model of what? Toy model of an index-like Cartesian function, but I don't really know what kind of index physically it is. By toy model, I just mean a generating function of integers if you make a series expansion. I want the generating function of integer, I mean simple toy model for that, in which the series of integers satisfy the following two properties. So for instance, you take a function, expand it, it will give rise to integers, and I formally call this exponent charge, and I want two conditions on my toy model. Okay? At large charge, I want the degeneracy itself to grow fastly, macroscopic. And secondly, I want it to behave like a typical index. Namely, the sign can be positive and negative, it can oscillate. With a little bit of trial and errors and thinking, the simplest example of this sort, which is solvable but still quite non-trivial, I think is what is called the inverse of Mac-Mahon function. So if you take inverse of this expression, this gives rise to, this gives rise to what is called the Mac-Mahon function. It's very, very long function in mathematical physics. It's a generating function for the three-dimensional Young diagram or the plane partition problem. So it's well-known function. If you consider the Mac-Mahon function, it just gives rise to macroscopic positive numbers. So I consider the inverse of Mac-Mahon function. Its definition is given in this way. So it has a minus sign here. So if you series expand in X, the coefficient can be positive or negative at various orders, depending on, because it carries various factors of this minus here. In fact, if you make a series expansion of this function to very, very high orders, it's very easy to do it using Mathematica, you really see that the numbers are macroscopically growing. Its absolute values are, how much is this? At 200th order, it's very, very fast growing. Even these numbers are very, very fast numbers. It's just exponentially fast growth, though, so they don't look as big as this, but these are also high enough, big numbers. So first condition is met. Second condition is also met. It's a large number with oscillation patterns. If you amplify this, it also oscillates with characteristic wavelengths. So two conditions are met by this toy model function. Okay. So the true entropy, true degeneracy is given by this for this so-called index, whatever it means. And I want to extract out this behavior by an analytic curve. Namely, I want to extract out this behavior by doing an analytic saddle point approximation of this quantity at large J. Okay? And I want to do it for the large number itself, and also want to do it for the oscillations. Okay?
Can I ask a question?
Yes, please.
In that plot, what are the two axes?
Oh, this plot. Okay, so this x-axis is J. Y-axis is omega J.
All right.
Oh, sorry, yeah. I thought. Is it okay?
Yes, thank you.
Sorry about forgetting the legends. Okay? So I want to get the same result by computing a curve trying to mimic this in saddle point approximation. Okay? So if you try to do the saddle point approximation of this integral, okay, you plug in the value of this, you have to extremize this. When j is large, the derivative of this term will be a large term. So in order to balance these terms to get a non-trivial saddle point at large j, this term has to be large by taking beta to be small. Okay? So at small beta, this can be approximated near the saddle point value by using this kind of series expansion, which you can easily get by using Euler-Maclaurin formulas and so on. Anyway, we got it. So you do the saddle point calculation with large j. Okay? And how can you realize these oscillating sign behaviors with macroscopic number? The natural solution, if you're good at saddle point approximation, getting an oscillating function like oscillating part of the area functions and so on, the natural way of getting it is to have a pair of mutually complex conjugate complex saddle point. Okay? So if you get one saddle point, you get the saddle point value of beta is complex, so its corresponding saddle point contribution to the index omega j will be complex. Okay? But this is a real integral. So if you have done calculations carefully, when there appears a complex saddle, there always appear a complex conjugate saddle. This addition will give rise to an integer. So not integer, but real number. Okay? So this expectation is really met in this model. The dominant saddle points come in pair of mutually complex conjugate saddle points. So these two contributions of this saddle point calculus takes the form of an exponential of something looking like an entropy, but this entropy is complex. So the saddle point is complex. Actually, this is the log of this complicated expression. You add these two terms, okay? And the conjugate pair terms has an exponential of complex conjugated formal entropy function, complex. So if you add these contributions, you get the two factors. First of all, the real part of this saddle point entropy function is common. You get an envelope function, which is exponential of the real part of this formal entropy function. And if you add the complex conjugate phase part, you get the cosine part, okay, of the imaginary part of the formal entropy function. So you perfectly realize a macroscopically growing number with the sine oscillations realized by this cosine oscillation. Okay? So this is a natural way of getting a macroscopic number which cosine oscillates. Okay? I want to show that this curve agrees with this numerical plot, completely. Yes.
Sorry. So your beta will also be complex on your saddle point. Is that right?
That's right. Yes.
And you will at some point give an interpretation for the imaginary part of beta as well?
Imaginary part of the beta.
The fact that this saddle point happens when...
You mean not imaginary part of this, but imaginary part of beta itself?
Yes.
And I think your question can be answered more naturally in grand canonical ensemble, right?
Right.
So can I postpone that to later part of my talk?
Thank you.
First part, I'm trying to interpret everything from microcanonical ensemble and deduce that chemical potential has to be complex. But in grand canonical ensemble, I think your question can be naturally answered. Can we come back to that later?
Sure.
Okay. So here, I'm very pragmatic. I have to reproduce this kind of oscillating behavior. So you have to get the natural way to achieve this is having a pair of complex conjugate saddles. So to have a complex saddle, it's natural to seek for complex data. So that's my involved logic at this point. Okay. So in order to show the match very, very impressively, I just don't do the leading saddle point calculus, but I computed all kinds of one of J corrections to very, very high order to see the impressive matching between the two in the next slide. Okay. So I don't really, I can plot the curve here, but this is too degenerate. So I decide to plot the log of that, the entropy of that. So this is a sine oscillating integer. I take absolute value, take log. This is what one can call is an entropy of an index. If you take this expression and just blindly take log, the first part will be giving rise to a contribution to the index of entropy. The second part, take an absolute value, and log is also contributing. Okay? But this is kind of stemming from the sign oscillation of the index. So it will have a relatively minor role. So let us first talk about this. Oh, before that, this curve I drew in this solid curves, blue and red, and I compare it with the log of this from my numerical data. So after including 1/j correction, these are very, very impressive match. You know, saddle point approximation is done properly, but we can extract out general lessons out of this. You know, there are many characteristic behaviors that you should remember from this simple toy model, and many of these behaviors will be repeatedly appearing in the more challenging, let's say, 4-dimensional maximal super Yang-Mills theory index and so on. So in order to make the point clear, I'm first showing the phenomena clearly in this solvable, easily solvable model. So I first pay attention to the second term, which is crucial for this oscillating, because of this oscillating behavior. If you just view this second term as a continuous function of J, which is actually not, J's are quantized, but if you just pretend it's a continuous function of J, because macroscopic saddle point approximation doesn't really know how this is quantized, the second term can hit minus infinity. When cosine accidentally becomes, cosine changes sign, because log of 0 is minus infinity. So actually, if we draw this plot carefully, all these dips here are, strictly speaking, hitting minus infinity. Okay. However, in practice, these curves should be understood at integer values of J or quantized values of J. So you practically realize that whenever this macroscopic degeneracy is about to change sign, when cosine is about to change sign from positive, negative, or vice versa, practically with these discrete numbers, you find that it's very hard for omega J's to get very, very close to 0 during sign changes. Let me try to explain to you what this means. So this area is the point where omega J's are about to change signs from positive to negative. Here, if you take a look, it looks very, very small, yeah. But it's not that small. You know, the numbers, these numbers are very big. It's just saying that these numbers are much smaller than this, maybe by a factor of 1% or something like that. This is not a small, very big difference. It may look like a very big difference if you just plot it this way, but if you take a log scale, the difference of this and this is not very large. Let's say some order 1 factors and so on. Right? So if you really get to the macroscopic regime, where this itself, the first term itself is going to be very, very large, you find that the second term is unlikely to contribute significantly. So in a sense, in the macroscopic approximation, the second term you roughly expect to be somewhat typically smaller than the first term. I can't precisely say how it is suppressed in 1/j fashion, because it's really naturally suppressed or improbabilistically suppressed or something. If you become very unlucky, who knows? I mean, you know, while changing sign, omega J's can be exactly 0, but it's quite unlikely to happen, right? You have quadrillion of numbers or zillions of numbers and it changes sign, exactly hits 0, it's quite unlikely, right? So in this sense, at macroscopic chart, we expect the second term to be much smaller than the first term. So we expect, of course, there are some unlucky outliers here and there, but as the charges become larger and large, I think this oscillation is definitely much smaller than its envelope function. So we expect that, yes.
So how does the period of the oscillation scale with J?
That depends on J, and that's very interesting information. It's actually a non-trivial function. You take a look. The leading behavior is this one. So it has, so the leading behavior is just exponential of this term. So it has a real part and imaginary part. The real part is this. You take imaginary part. So the leading behavior of imaginary part is J to the 2/3 or something. J to the 2/3. So what does it mean? It means as J grows, the wavelength increases. You see this, right? Because it is a cosine of J to the 2/3 plus blah, blah, blah. If it had been cosine to the J, the period will be constant, right?
Right. But now suppose you compare the period of this oscillation with the rate of change of the real part. So the period of the oscillation with the exchange that you have to make in J for the real part to double. Is it small? I mean, is it oscillating on a small scale compared to the real part in some sense?
Small scale means this vertical.
No, I mean, is the wavelength of oscillation small in units of the distance it takes for the real part to, let's say, double?
Real part double significantly changes, you mean?
Yes.
Let's see. The period will be taking derivative of this. Sorry, what is it? The wave number. Wave number, it will be a derivative of this with respect to J, so that it's constant for this. So it's something like this. The wave number is this. So lambda is something like J to the 1/3, J to the 1/3. And the real part is scaling like this. So if it doubles, how should I say? By the way, why are you asking this question? Can I ask?
Because I would expect that only when the wavelength of this oscillation is small compared to the scale of that to happen, that it leads to big cancellations in a naive computation.
Sorry.
It oscillates fast for you not to be able to see it if you're doing things naively.
Oscillation is fast. Sorry, say again.
If it oscillates fast compared to some natural scale, then if you do things naively, you might get zero, or you might see much smaller growth, like actually happened in the superconformal index. If it oscillates, on some very long scale.
Well, I think it's really, if this oscillation period is small, you can clearly see this oscillation period here because the wavelength is quite macroscopic. But even if the wavelength of oscillation is very small, you may get something like this.
No, wavelength is small will clearly obscure things. I'm saying wavelength becoming too large.
Let me say it this way. If wavelength is small, a macroscopic Legendre transformation would not clearly identify it. Okay? So in that sense, I would like to say that, if the wavelength is large, this cosine part can even predict this wave patterns convincingly. But if the wavelength is small, this factor gives something, but it's beyond the validity of macroscopic Legendre transformation. So this factor in this case of small wavelength should be interpreted as an ambiguity factor, I think.
Right, but I was thinking that if there was oscillation on some very long wavelength, then simple-minded approximations, it would not ruin simple-minded approximations.
What do you mean by simple-minded approximation?
Like
this is simple-minded, right?
Just naive Legendre transforms. Not going off the real axis, for instance.
Not going off the real axis. Oh, you mean when it's positive for a long while?
Yes.
Then
there's no real cancellation and nothing funny should happen. I feel there should be a sense in which the wavelength is smaller than some other length scale, which is what, at least in the superconformal index.
Okay, my feeling is the following. So if this wavelength is very, very long,
yes.
So that in very long, no, you shouldn't go this way. So let's say if the wavelength is very, very long, so very, very long like this. And in these regions, the usual Legendre transformation without complex beta could approximately give the right result, right?
Exactly.
So in that case, what I would naively expect is that the saddle point of value of beta will have much larger real part than the imaginary part.
Right, and in some parametric limit, the saddle point would be real.
Yes. Does that make sense?
Yeah.
I have to check. I have to check whether such examples exist, but that's my expectation. Yeah.
Yeah. So there must be a sense in which, at least in the superconformal index, this wavelength, while possibly large, is smaller than some other scale.
Possible. Yeah.
Okay.
I think so.
Well, sorry, one more related question. This,
yes.
If you looked only for real saddle points or integral, would the only saddle point be x equals 1? What would the
the real saddle point is a subdominant saddle point. Can I explain this here? So let me explain the saddle points in the leading order. So you have to balance this and this, right?
Yes.
So this is the leading order term of the second term. So if you take derivative of that, you basically have J, take beta derivative, and plus something like, what is it? 3 zeta function, beta cube equal to 0. That's the leading order saddle point equation. So beta cube saddle point value is a negative number. What is it? minus 3, no, sorry. Minus 3 zeta divided by j. So there are 3 roots. One root is real negative root, right? Because you just take cubic root of this. And 2 roots are the complex conjugate pairs. If you plug in the real root, it gives the subdominant contribution. And the 2 complex roots are giving rise to dominant contribution, meaning the real part of the dominant entropy function, a real part of this entropy function is macroscopic.
Okay. I'm trying to find the analog of what we did wrong with the superconformal index. Our saddle point there was just x equals whatever, 1, right? You know, we were just expanding around the uniform saddle.
Yeah. Uniform saddle. But that's a saddle in the grand canonical ensemble, right?
Yes. Okay. We'll come back.
So grand canonical ensemble issue, I'll try to address later. But I mean,
thank you.
I mean, the grand canonical issue is not completely resolved, but there are very recently interesting works by Komagorski and company, which I think basically suggest the answer. So let me try to comment on that later.
Okay, thank you.
Okay. Sorry. I'm postponing too many things, but if there are other questions, please interrupt me. I'll try to manage with time. Other questions? So anyway, the lesson I wanted to draw is that there's an oscillating pattern, typically smaller than the envelope function, and that's because of this probabilistic unlikeliness for omega to hit close to 0. So it's a strange reason, but you expect this oscillation to be smaller. But the reason for this oscillation for these dotted numbers are the oscillations of these macroscopic indices. So whenever this kind of feature happens, you have to remember that it's related to the oscillation of the macroscopic index, and it's also related to the complex pair of saddles in the Legendre transformation picture. Okay. Yeah, that's all I wanted to say with this toy model. And next I'm going to move to more challenging example, the index of the 4-dimensional maximal super Young-Mills. Actually, it's the radially quantized quantum field theory, so it's given a mass. So it's really looking like a thermal partition function of the quantum field theory in the BPS sector. It has an analog parameter of temperature, although it's not real temperature, and you can weight the states with 5 charges appearing in this maximal super Young-Mills that BPS states can carry. So you can have 3 R charges, you can have 2 angular momenta. So you first start to introduce 5 chemical potentials for that, which I call delta 1 to 3, omega 1 2. You have minus 1 to the F, you trace over it, it becomes an index. And these authors have paid very careful attention to make this a Witten index, independent of coupling constant, so that you can trust the result all the way to strong coupling. For my personal view, I'd like to slightly change the convention of writing down this index. Oh, sorry, before saying that, in order to make this an index, apparently you introduce 5 chemical potential, but you have to demand this weight factor appearing in the trace to commute with the supersymmetry that is implicitly associated with this index and BPS states. So in order to fulfill that, demanding that this factor commutes with some supersymmetry, you have to impose a linear relation of these 5 chemical potentials. Let's say this, okay? So that the independent chemical potentials that can be carried by the index is 4. Now I want to slightly rephrase this by changing the convention for the chemical potential by making certain imaginary shifts. I want to absorb this minus 1 to the fermion number into a complex shift of any of these 5 chemical potentials. And that's doable, especially for maximal Young-Mills, because minus 1 to the F can be written as an exponential of a spin quantum number multiplied by suitable coefficients. And that's possible because all these R charges and spins are just spins in 10 dimensions. So if you evaluate any of these 5 charges, they are half integral for fermions and integral for bosons. So if you have any of these 5 spin quantum numbers, minus 1 to the F can be written this way. So minus 1 to the F can be absorbed by certain 2 pi I shifts of any of these 5 chemical potentials. So you apparently get rid of this minus 1 to the F, but the effect of this minus 1 to the F is reflected by this shifted relation of the chemical potential. I like this convention because partly because it maximally emphasizes the fact that -1 to the F is essentially a complex chemical potential. And the Legendre transformation and all this issue is trying to find the most dominant, most efficient way of, how should I say? To find the dominant way of distributing this 2 pi I to all these chemical potentials in a certain manner. So it makes it natural that the static points could be just naturally complex. And it also emphasized the relation that -1 oscillation is related to this kind of phase oscillation caused by complex chemical potentials and so on. So I like this convention, which I'll use frequently. And at the next slides, I'll make a small historical remark. But recently, from 2 years ago, many groups of people.
Hello?
Yes, please.
Hello?
Yes.
Yeah,
Hello.
sorry. Can you explain where does this mod 4 pi I come from? I mean, usually you just take all of them to be real, right?
Oh, this mod 4 pi I. You know, if you have in mind that all these charges are half integrally quantized, you know, any chemical potential is equal to it shifted by 4 pi I. So this relation is also holding mod 4 pi I. So just because all the spins are half integrally quantized. 4 pi I is a periodicities of all deltas and omegas.
Okay.
Is it okay?
So I mean, you're just you're not making the statement that if I kind of let's say slowly vary it, give an imaginary part and increase something by 4 pi I, in principle, something
you mean
like
continuously change it from 0 to 4 pi I?
Yeah.
Oh, no, that cannot be done. Then in the intermediate stage, it's not an index.
Right. Okay. So that can give something like a spectral flow or something. So you're not saying that. You're just saying that.
No, changing 0 and 4 pi I is a discrete thing. It's like a large gauge transformation.
Okay.
You know, never continuously, never. Yeah.
Okay. Thanks.
Okay. So you know, this was a notorious object ever since the first finding of in 2005. But somehow people managed to compute it quite interestingly by various methods and approaches 2 years ago. And there's a long story in each group, but oversimplifying the story a lot, the calculation boils down to deriving the Lagrange free energy of this partition index given as follows. So at order 1 chemical potentials is n squared, so it's really looking like the black hole free energy. And all calculation boils down to deriving this in this convention, okay? And this is an important quantity. Actually, this importance of this function has been noticed before anybody computed it, okay? So, it's a very, very interesting to me. But these people, Hosseini, Christoph, and Zaffaroni, roughly 1.5 years before this paper appeared, found a marvelous observation that if you start from this function, satisfying this constraint, and if you suitably Legendre transform into charges, you get, after certain manipulation, you precisely get the Bekenstein-Hawking entropy of the black hole. That's the thing they found. If you start from this function, do Legendre transformation, so-called, I mean, it's a little bit mysterious, you get an entropy that equals the black hole entropy, okay? So from this index, if you have successfully computed this, you get a way of explaining the black hole entropy. So anyway, all the calculation boil down from this. I'm not going to talk about this calculation. I'm going to talk about a more interesting calculation done by these authors, which is roughly the Legendre transformation. I mean, it is an Legendre transformation. But, you know, I remember the first time when this shocking paper appeared in 2017. At least I couldn't understand what's going on at that time, because some of the recipes of computing things are inspiring, but it was very mysterious. Eventually, I cooked up my own way of understanding this, which I'll phrase. And depending on who are you asking to, I believe different authors have different opinions on how to interpret this Legendre transformation. And I think all viewpoints have good reasons to respect. But anyway, I'm telling you my interpretation, which I think is supernatural, especially having in mind a toy example of the McMahon inverse function, which I showed to you. So anyway, let me tell you my story. So apparently frustrating thing is that if you Legendre transformation with this constrained chemical potential, 4 of them, with 4 microchemical charges fixed, you get an entropy. You're supposed to get an entropy, which depends on these 4 charges carried by the index. But the frustrating thing is that the saddle point of this Legendre transformation is always going to be complex, right? You know, this is complex constraints. So at least one of these, some of these 5 have to be complex. So it's naturally a complicated complex number, dividing this 2 pi I in a complicated way to these 5 variables. And the resulting entropy plugging in this saddle point value is also complex. Okay? So apparently it's confusing, but now in my viewpoint, especially with the toy model exercise, you know what the natural picture should be. There should be another complex conjugate saddle point, right? Because, you know, the underlying quantum field theory is unitary. The result should be a real number. So we expect naturally the existence of the second saddle point related to the one that has been found in this paper, so that the net entropy of the index is given by the similar formula that explained this toy model. Yeah, right? So I'm going to establish this one by one concretely in the context of n equal 4 Yang-Mills. Okay? So before doing that, let me give a very brief historical remark, because this has been a quite notorious problem for more than 10 years. And the heroic effort started from this paper, the Kinney, Maldacena, and Shiraz and Suvrat, 2 of them are here. It's also done, the index was established at a similar time with Romersberger, but the motivation of this paper, I think, was just to understand the dual AdS5 black holes, discovered by Butovsky and Rare and people just 1 year ago, okay? more or less. The thing is that I try to emphasize the role of complex L's and complex fugacities, but you know, naturally people thought of doing normal thermodynamics at real fugacities. Okay, so in the old days, people tried to understand the behavior of this macroscopic index with at real slice of chemical potential. Okay? And all the papers that I'm going to mention here are actually done in the grand canonical ensemble picture, so it's not coherent with my microcanonical picture. But anyway, it's a historical remark, so let me just phrase it. So they try to find in the grand canonical ensemble what is called the deconfinement phase transition. Okay? Some of these details I'll sketch later. And this is a real hallmark of seeing the black holes in the grand canonical ensemble, following the strategy of Witten and Aharoni and collaborators. But somehow at real chemical potential, in retrospect, they couldn't identify the proper deconfinement phase transition. So it seems that black holes couldn't be found. Some years later, I mean, apparently this seems to have nothing to do with these black holes, but they eventually turned out to do similar things. Di Pietro and Komogowski studied this superconformal index for general n equal 1 superconformal field theory when the temperature-like parameter is taken to be large. So it's a kind of Cardi limit in the higher dimensional theory. Okay? High temperature asymptotic behaviors. Okay? Apparently it has nothing to do with the large and free energy, but if temperature is taken to be large, and central charge also large as well, this approach could have discovered the black holes at a point, black hole physics, when the black hole size becomes very large and hot. Okay, so if you take central charge large together with this high temperature limit, you can see hopefully large black holes. But they again did the kind of limit where the inverse temperature-like variable is taken to be small, all at the real slice. And a little bit frustrating result was that they got a free energy which scales much slowly, which grows much slowly than the naturally expected one. This 1 over beta, the linear growth in temperature, is not really the fast growth that one would naturally expect for the index. Actually, it's 1 over beta square that we have clarified recently. A more frustrating fact is that for n equal 1 theories, the coefficient is given by the difference of the 2 central charges, C and A. So the theory with gravity duals have C and A equal at the leading order. So even if the central charges are both proportional to n square, this subtracted quantity will be much, much smaller than n square. So this is a second frustration. Okay? And now we can interpret all these results as occurring from the fact that they worked on the real slice only. Okay? So we're going to reinvestigate this question, having in mind that the index can be actually macroscopic, but with sine oscillations, with suitable wavelength, as Shiraz mentioned, so that you really have to consider the complexified saddle point of betas and omegas seriously. Okay? So I'm going to first show some empirical evidence for this sine oscillating macroscopic behavior of the index. Then, if this is true, then we should seek for the complex saddle points, which the pair of saddle points, which will realize this oscillating pattern by this cosine type function. Okay? And having this in mind, that you're going to seek for the saddle point in the complex plane, you first have to compute the free energy of the grand canonical ensemble, taking these chemical potentials to be suitably complex. Okay? And this third point, I've already explained, it has been taken care of by all three groups when they computed this. So the third point I sort of explained, people took care of this third point. The first and second point is the logical ground of this third computation. So I'm going to explain this now. It's okay.
So could I just one second,
Yes,
please?
Yes.
Just going back to your McMahon function.
Oh, yes. Yeah. Plot or the formula?
The formula, please.
Yeah. Yes.
Yes. Your McMahon function was defined as omega j x to the power j.
Omega j.
Yes. Now, if you get a complex, if the phase of x turns out to be complex at the saddle point, it would at least naively suggest that if you add that kind of phase, that compensates for the phase in omega j.
Yes. In the grand canonical picture, I think that's the picture. You know, let me just say it now. My understanding of the grand canonical ensemble is the following. You know, if you just take real x's and if omegas are macroscopic number just oscillating, you know, it'll undergo vast cancellations or smearing of the nearby term. You know, it's really like a fastly oscillating integral becoming very, very suppressed, right?
Yes.
So sine oscillation of omega, if you can try to interpret a certain kind of phase with certain wavelength, an optimal choice of the phase of x will be to provide a compensating phase, okay, as a function of j.
Good. So
yeah, but this but this compensating phase, look, but this compensating phase is always linear in j, right? So if the phase oscillation of this omega j is also having a constant wavelength, this can balance this in all regions of charge space. However, in many cases, the wavelength of the sine oscillation for this omega j changes. So in that case, the optimal phase choice that you have to make for x will depend on which charge regime you want to really probe.
Perfect. So, but then, you know, so that would seem like a second way to get an estimate of the wavelength of oscillation. Right. Once you know the imaginary part of you write x as e to the power mu, and you know the imaginary part of mu as a function of j. That should tell you how fast it's oscillating there. But you also had another.
I think that's basically somehow reflected here as well, right?
That's what was confusing me. Here, this is the imaginary part of S of j, whereas that would have come from the imaginary part of.
Okay, let me think of this. Let me see. So imaginary part of S of j. I'm just doing. If you take derivative of this gives rise to a wavelength, which is k. And in thermodynamics, what is this definition? Is it related to the imaginary part of beta or whatever?
Yeah.
You know, chemical potentials are related to entropy by some derivatives and so on, right?
Right. Okay, great.
So great. I think there's a chance for this to be related at saddle point.
I see. Thank you. So that would be another way of getting the oscillation frequency, right? Just find the imaginary part of the temperature or the inverse temperature, and that will also allow you to compute the oscillation frequency.
Yes.
Thank you.
Thank you. By the way, Joel, is ICTS strict about the time limit?
No. It's not strict at all. So you can go on.
Nowhere in India I've experienced strict time limits. So okay. So
yeah, sure. Go ahead.
Okay. So I can be a little bit more flexible at the time, right? Okay.
Yeah.
Well, let me go ahead.
Yeah, sure.
So anyway, I've given a roadmap I'm going to empirically check, at least with some example, that the index for the maximal supernomials also grows macroscopically, but with sign oscillations. And then I'll establish, and I'll just carefully reinvestigate this Legendre transformation calculus again, which has been basically all done by Hosseini, Christoph, and Zaffaroni 3 years ago. Just carefully reconsider it according to my flavor. Yeah, I'll do that to establish my interpretations about real parts and imaginary parts and cosines and all that. So first of all, index sign oscillates. You can just check it brutally. Okay, the best way of checking it is just expanding it in fugacity. But unlike the McMahon, it's a bit tricky because if you take a UN maximal supernomials, its index as a function of fugacity is given by this unitary matrix integral. This is also derived in the paper by Shiraz and company, also some years earlier by Bose-Sundberg and so on. Okay? And it's a 4-parameter fugacity function, so it's complicated. So I decided to unrefine, essentially keeping one fugacity conjugate to this combination of charges. And this fugacity is playing the role of roughly temperature, roughly. Okay? So I brutally expand this, okay, on computer, because I don't want to use my brain at this business. So I just brutally expand it on computer and brutally do the integration. I cannot do it for large n because computer doesn't know it. So I do it for reasonably large n. Yeah, I mean n equal to 5 or 6 or so on. That's what we did. So expand. This was done by our group, Agarwal's, my student Che, Seok Kim, Jun Namgo. A coordinated paper which appeared on the same day was written by Samir Murthy, who did the same mathematical calculus. You know, 5 of us gathered to get U5, U6. Samir alone did U10. I mean, this is, oh, this was the most shocking experience of myself this year. U10. I want to follow this calculation, but anyway, U5 or U6 is good enough to confirm the expected behavior. No, these are integers. At 100 charge order, this is 10. This one is 10 quadrillion. It's a huge number. You see that it's an expected growth. So it's macroscopic enough, and you see that it sign oscillates as well, quite chaotically. So you see that it's a macroscopic number with sign oscillation as well. Okay. So in order to see that in a more quantitative way, I plot it. Again, I plot the absolute value of the index and take log, and I plot it. These are the dots for U5, and these are dots for U6. In order not to forget the sign information of the oscillation, I color the dots in different way. I massage the sign oscillation a little bit so that the wavelength of it becomes sort of macroscopic, so it can be easily more predicted by the Legendre transformation calculation. If you just stare at the sign of omega, they change much more rapidly. If you make a redefinition of chemical potential, change x into minus x, so effectively if you dress the index by -1 to the j, then the wild oscillation, small wavelength behavior, becomes somewhat more flattened. So investigating the sign of this is, I think, the most interesting thing to do, especially in the Legendre transform. So anyway, I plot the sign information of this. When the color is red, this is positive. When the color is blue, the number is negative. The wavelength is quite large. It's of order n. It's of order n. Okay, it's almost n. So it's quite macroscopic, if you believe n to the 5 or 6 is large. So anyway, the behaviors are quite similar to the Mount example. You know, first you have an envelope function, and this envelope function is not black curve. The black curve is actually the area law, Beckington-Hawking entropy of known black holes, in which I blindly inserted n squared equal to 25 or 36. I mean, sort of trusting that 25 is fairly large enough, and so it might be somewhat trustable, right? So this is the black hole entropy curve with this blind substitution, and when the charges are macroscopic so that black hole solutions are reliable, I think the match here are quite impressive, right? But this is not really my interest here. I really want to understand this detailed oscillation patterns and so on in order to establish my interpretation of and confirm my interpretation of the Legendre transformation. Okay. So the conjecture. Yeah.
Sorry,
yes?
so did you have an interpretation of this x goes to minus x, please?
Oh,
Why was it
this
positive?
factor, this factor.
Yes.
Hmm.
Not just some boson fermion kind of. I mean, was it something simple, or do you know why?
Oh,
why
so physical interpretation.
yes.
No. You know, it's somehow changing the effective notion of bosons and fermions. So I was once obsessed by the fact that the sign oscillation becomes so simplified after this. I mean, having a long plateau of positive number and negative number. So according to this convention change, you can effectively distinguish the field theory letters into effective bosons and effective fermions, right? So I've played some time. So you're asking about this kind of physical interpretation, right? Am I right?
Yes.
So I don't have a conclusion, but I see a very curious patterns, right? So well, if time is okay, I'm just going to tell you. So I'm strictly following your convention. So this is the gaugino, which is fermion. This is the chiralino. Also, so this is for the people who just understands the notation of Shiraz and Subrat. So this is the antichiral boson, and it can be addressed by some BPS derivatives. What else do we have? There are field strength. Is that all? Yeah, I think that's all. So these are fermions and these are bosons. But if you make this effective extra -1, insert extra -1, the effective bosonness and fermionness, I mean, the letters are counted with either plus sign or minus sign. So the letters which are counted with plus signs, I think, are this. Plus sign. This is counted with plus sign. Let me think. I'm not sure about this, but these are counted with plus signs, although it's fermion. This is counted with minus signs. This is counted with minus signs. I'm not sure about this. So the curious interpretation is the following. If you consider AdS 5 times S5, in this change of minus plus notation, the modes which seem to be the super translation modes in AdS 5 seem to come with minus sign. You know, derivative is translation in AdS, right? Or S5, S3. Psi, I think, can be the super partner mode of the superparticles moving in AdS 5 with respect to certain supergroups. This seems to be the internal modes in S5, you know, in various senses. If you consider chiral rings, which are internal excitation, they acquire contribution from this. The other space-time modes in AdS 5 counted with minus sign. So that's a curious observation I have. I don't know what physics it is. I once thought that it might have interpretation in terms of giant and dual giant gravitons and so on, but I've never made the story complete.
And just more simple and just completely simple-mindedly, does it mean that if I look at the spectrum of n equals, the supersymmetric spectrum of n equals 4 Yang-Mills, at one energy or one, you know, E plus J, it's more bosonic than fermionic, and the next energy it's more fermionic than bosonic, and so on.
Well, I don't think this, I mean, the simplification of sign oscillation with this change, I don't think this is a very intrinsic property. I think this is a property which happens in the intermediate range of charge. You know, if you go to extremely, extremely large charge range, J being much, much larger, so that if you enter the Cardi regime, this simplicity will break down.
Because but in the black hole regime, it's true?
You know, well, this is the black hole regime, and the Cardi limit is also the black hole regime. Large black hole, intermediate size black hole.
No, but I mean, black holes of order, energy is of order n squared times 1.
Oh, you mean typical size black hole?
Yes.
I'm not sure. I mean, this behavior might have to do with the fact that n is large, fairly large, but not strictly large. So
you're saying it may be an artifact of finite n numerics.
Perhaps. Finite n and some energy levels related to this value, choice of value of n and so on. So I don't really think it's very intrinsic property, but yeah.
Sorry, one more related question. If you just look at the superconformal index of the gravitons, so we're at large n, and we just look at the multi-gravitons. In that, do you see a similar rapid oscillation?
They're all positive. You know, these first red numbers here, right? These are the graviton regimes.
Yes.
So if you change the convention, graviton index in this one figure ST convention on refinement is all positive integers.
But you need to do this -1 to the power j for that?
Yeah. After doing that, so that's why the first few dots are all positive. the low energy spectrum below certain threshold, you know, it's dominated by gravitons, right?
Right. So
So after the, yeah.
Yeah, for the multi-gravitons, it's true that at one E plus J, it's mainly bosonic, and the next E plus J, it's mainly fermionic, and so on.
Yes. So if you just work with omega J convention, it's blue, red, blue, red, blue, red, just strict alternation.
And that's just an exact result at large n, right? I mean, it's true at large n.
I think so. Yeah, I think so. Yeah. I think so. Yeah.
Thank you. Yeah.
Although I don't know what it means.
Yeah, interesting. Thank you.
Okay. Thank you. So where was I? Yeah. So I was trying to reproduce this. Yes.
So this oscillations you said depends on n. Is it a power law in n? This gaps between
sorry, say again, please.
The gap between the blue, the length of the blue and the red.
If it's horizontal duration.
Is it a power law in n or?
That's roughly n or n plus 1 or n minus 1. I mean, it's plus 1 or minus 1 depends on which colors assume that is deep.
Okay, so it's linear in n. If n.
Yes. Well, if n equal to 5 is a large number.
Yeah, n equal to 5 is a large number. Okay.
Yes.
Thanks.
Yeah. It's curious numerology, but I really failed to interpret. Yeah. Eventually, I was initially obsessed by these findings, but eventually I thought that this is an accidental behavior in certain finite n and certain range of charge or so on. So I don't know. Yeah. So anyway, the next goal is to just do the Legendre transformation carefully and reproducing this small oscillation by using the entropy formula. Let me go through this step a little bit quickly. This is basically repeating the Hosseini-Christoph-Zaffaroni convention and calculation. It's basically the same concerning the real part, but you have to be extremely careful about the imaginary part because you want to really reproduce this oscillation and wavelength and so on. Okay, so I paid a little bit more attention to the imaginary part. I mean, being strictly sincere to my conventions and so on. So the imaginary part of the calculation is trivially different from this. But anyway, the calculation is done. You extracted out this cosine part, you take log, you plot it. It's showing fairly, I would say it's showing fairly good agreement between the saddle point calculus is oscillation from this and the numerical dots. The reason why the agreement between dots and curves is not that nice is that for the case of McMahon functions, we could compute all these 1 over j corrections. So we could make this agree very, very well. In this maximal superannual side, unfortunately, we only do the leading contribution. Well, maybe in some recent papers, subleading contributions are computed, but at the time of writing this paper, we didn't know how to compute the subleading contributions comprehensively. So that's the reason why the agreement is slightly uglier. But still, you see that, you know, this Legendre transformations oscillation due to the two complex conjugate saddle point is giving rise to an explanation of this small oscillation. But anyway, for the same reason, this small oscillation given by log is actually small. The basic reason is that Sj is a macroscopic number. So this is macroscopic. Imaginary part is macroscopic, but cosine of macroscopic number is no longer macroscopic. So it typically gives a small result. Okay? So we should expect that real part of this complex entropy function is to be giving us the dominant contributions of the entropy if we can ignore this small fluctuation. And in fact, this real part as a function of single charge J equals the Beckington-Hawking entropy of the original Gutovsky rare black holes. And this story can be generalized to the most general case in which the black holes carry 5 charges so that the index can be seeing 4 combinations of them. Entropy as a function of 4 independent charges, again, completely agrees with the black hole entropy if you take this real part. Imaginary part is giving you this oscillation and sign information. Okay, so that's precisely the same structure as McMahon function. Now there's also an interesting story of interpreting the same calculation of Hosseini-Christoph-Zaffaroni in still a mysterious way now in my thought. They say something, who said it? I also said something like that, but they say, I mean, some people say interesting fact about vanishing of the imaginary part of this extremized entropy function for describing particular black holes, single center black holes of particular source and with enhanced near horizon symmetries and so on. So there is a very interesting line of arguments and thoughts along that way, which is slightly different flavor to what I told you today. And that's a good observation. I really love it, but it's a kind of mixing the intuition between gravity and field theory. So, well, it's basically, I think, the arguments given by Benini and Milan's paper, this I-extremization business, based on earlier works on topological black holes with Zaffaroni, Christoph, Hosseini, et al. I'm just affectionately staying at this idea to, well, there are some fascinating alternative statements about the same calculation, which I really didn't say today. Just to be fair, let me emphasize that. Good. I ran over time, so I'll be a little bit quick. So I'm going to give a picture on the grand canonical ensemble. So, I mean, strictly speaking, it's mostly related to the pictures in microcanonical ensemble, but it's worthwhile to discuss the similar phase oscillations and so on intrinsically in the grand canonical ensemble. Okay? And also it will have some interesting physics in grand canonical ensemble. So if you just stay at this grand canonical partition function, keep this x to be fixed, let's say real number. This is already what I said during Shirazi's question. Suppose that this number, omega j, is macroscopic and severely oscillating, okay? And suppose that x is just real. Then, I think my intuition is that a fastly oscillating integron, with this being sort of integrand, is receiving a severe destructive interference so that the integral is becoming small. I think the summation of a fastly oscillating integer, even though individual integers are large, will be could be severely underestimated due to the cancelling, or more properly saying smearing of a nearby term, summing. Okay? Or let me say the destructive interference, borrowing this language. And that can be remedied, I mean, at least partially, by introducing some phase factors for S, which will partly, at least partly, try to flatten the wild oscillation that you see in this integer part. Okay? So this is kind of wavelength and oscillation. This can be providing some counter oscillations, at least for a particular range of J's. Okay? So that's the reason why when you turn on the phase factor of this Fugasti and tune it to a favorable value, you can certainly start to see a hidden physics. You know? If you don't turn on Fugasti phase or turn on bad values, smearings will still exist, and the true physics hidden in the index by this macroscopic number could not be seen because you've chosen the wrong value of Fugasti. The game is to choose the nicer values of Fugastis, okay? And to see. For instance, if you're going to see some interesting phase transitions increasing the temperature, if omegas are growing fast as a function of energy J, they can cause interesting phase transition, which will be the Hawking phase transition as you increase the temperature. But if the smearing effect happens, the existing phase transition can be apparently be invisible or in somewhat delayed due to the smearing effect. So the true Hawking phase transition can happen in certain temperature, but if you choose a bad value of phase, the apparently visible transition temperature might be higher. It's just apparently looking higher than the true transition temperature because of this unwanted smearing effect. So you want to obstruct this smearing effect maximally by tuning the phases carefully and see as close as we can get to the true transition temperatures and so on. So the important transition in this game is the Hawking phase transition. And let me just fastly go through things. It's very technical, but I don't have time to explain. In the larger limit, these people have shown, and it's also well known in the matrix model literature, that the maximal Superconformal index can be written as a functional integration of a distribution function. Okay? If you remember a previous formula, n-dimensional integral formula, the integral values are eigenvalues of a unitary matrix. So these eigenvalues are living on a circle. The larger limit, the number of these eigenvalues becomes very large. So you can one-to-one map the integral variables from large number of eigenvalues to a functional integral. Since it's a distribution, It's constrained to be non-negative, so it's a constrained functional integration. Or in other words, you can make it into a Fourier modes functional integration for this variable, where these variables should be constrained by this constraint. But anyway, if you write this index in the larger limit using the Fourier modes of distribution, the bulk integrand is simply Gaussian. And this function is a function of chemical potential. We call it roughly letter index, single particle index. So in this kind of picture, these integral variables, rho n's, behavior at the saddle point becomes very important for determining the phase structure of this index, partial function. Namely, you have a Gaussian integral. If the Gaussian coefficient f is positive, the saddle point will be around rho equals to 0. But if the chemical potentials, temperature increases so as to change the sign of this Gaussian coefficient, it will suddenly become a flipped Gaussian. And this corresponding mode will want to condense to a maximal value, because that's preferred, to a maximal value allowed by this kind of constraint. So if this value of if some of these modes omega want to condense because of this Gaussian coefficient flipping sign, we say that this direction, this mode develops a tachyonic direction. It wants to condense. If this condenses, its free energy is going to be macroscopic and proportional to n squared. And so that will be the free energy of the large black holes in AdS. And the Hawking-Page transition has happened. For the field theory language, this is a deconfinement phase transition. And this is supposed to be the field theory about the Hawking-Page transition. And in this old story of ordinary partition function and not index, the tachyonic condensation of any of these modes is directly related to the deconfinement transition. Okay? And normally it turns out to be this first Fourier mode, which first wants to condense. But in our model, it's becoming subtle with vigacities. If it's an index, if it's a complex vigacity, this coefficient is complex. Right? So whether this mode develops tachyonic direction or not is to be answered by investigating the real sign of the real part of this coefficient. If the sign of the real part is positive, if rho becomes larger and larger, suppressing measure will be obtained. If this is negative, rho being larger and larger will yield a very large real part. So let us first decide in which cases tachyonic directions are developed. Okay? And we're going to investigate in the full complex vigacity space. We're going to promote x to a complex number. So in this convention, let's regard x as the absolute value of complex x and phi as the phase. And as a function of real vigacity and the phase part, I make a contour plot of this Fourier coefficient for the first one, because this is the first value which wants to constrain. This is the contour plot. This boundary of the dome is the point where the real part becomes 0. Inside the dome, the real part is negative, so rho 1 develops a tachyonic direction when the temperature becomes high enough. Outside region, the real part is positive, so no tachyonic directions are developed. Especially the earlier work pioneered by Shiraz and Souvrat and et al. Studied this behavior at real vigacity, at this line. On this line, this is just always positive. This is always positive. Okay, so that's the reason. If you don't turn on the phase, the index is macroscopic, but the smearing has appeared severely, so that the tachyonic direction or the transition temperature has been infinitely delayed all the way to infinite temperature. But if you turn on the phase in a clever way, you approach certain region like this, and x approaches this threshold temperature, and you suddenly enter into a tachyonic region. So similar tachyonic condensation could be expected. The question is whether it actually happens and whether it actually leads to deconfinement. Okay? This is a very subtle question. Okay? When I first observed this tachyonic
hello?
Yes.
Hello. So the midpoint between these two lobes is 2 pi, phi equal to 2 pi. Is that or?
Yes, this is 0 to 2 pi. It's 6 point something, so it's 2 pi. Yeah.
Okay. So the midpoint is pi. Is that?
Yeah.
Is
Pi,
symmetric
This is pi.
about reflection about phi equal to pi.
Yes, that's right. It's reflection symmetry. Yeah, and the 2 pi is actually the period.
Okay.
Yes. Good.
Okay, thank you.
Yeah. So I first observed this tachyonic direction almost 2 years ago. Well, maybe I was fooled for the last time by this complex fugacity. I told you at the beginning, if you're careless, complex minus ones in the index can fool you all the time. I thought I overcome this kind of obstruction, but again, I was fooled 2 years ago, I think. At that time, I was not quite confident that, oh, in the partition function, tachyon was the confinement, so probably that's true in the index as well. But it's not, it's very subtle. Because the chemical potentials are complex, the effective actions for these variables are again complex, and everything becomes subtler. But anyway, let me try to explain to you why I was wrong and how my good colleagues suggested a very natural resolution. So 2 years ago, basically my intuition was stemming from this one-dimensional truncated model. Okay, it's actually an infinite dimensional model, and it's a constrained integral. So these integral has to be made in an open region with boundaries given by this constraint. But if it's complicated, but if you just get simple-minded and maybe, since rule one is most important, truncating it blindly to one-dimensional model might capture some physics. You can just consider this unjustified one-dimensional truncation, okay, ignoring all the mode. In this case, tachyonic direction, the tachyonic point is the deconfinement point in this model, okay? If this sign flips for the real part, rho being 1 suddenly wants to get condensed into its maximal allowed value, making the free energy macroscopic, and it deconfines. And then this tachyonic line, black line, which is an amplified line of this red line here, this one is amplified, the black line. This will be the truly deconfinement line in this one-dimensional truncated model. Then we see a little bit of puzzle because we compare it with the Hawking-Page transition line. It's an index, so there's no excuse for having discrepancy. It's not weak, strong coupling interpolation. Everything should match, right? But if you see the Hawking-Page transition line with the complex fugacity space, it's the solid blue line. Solid blue line. So it's substantially higher than the tachyonic direction if this is the deconfinement line. Okay? So this is a quite puzzling thing. Dotted lines, I won't explain. So at that point, I was too brave. If you see a mismatch in particle physicists predict new particles, I wanted to predict new black holes. So, maybe there could be new black holes whose Hawking-Page transition temperature will be substantially lower than this, matching with this. I thought it was a natural resolution, but this was a fake conclusion that I got from this one-dimensional truncation. Very recently, 2 months ago, Coppetti, Grassi, and Komagosky and Tiziano wrote a very, very interesting paper pointing out what could be going wrong in my quick conclusion. They have found, now I'm reinterpreting what they did in completely my language. Essentially, I'm borrowing their idea, but I'm phrasing in my own preferred language. Essentially, what is going wrong is that one-dimensional models deconfinement is different from multidimensional integrals deconfinement. Okay? Suppose that you integrate things one by one. If rho 1 integral is all, and if rho 1 condenses if f becomes negative in the real part, that's it. You're going to have a macroscopically large free energy, having large and positive real part. Of course, you have a fast oscillation. Of course, you have a macroscopic imaginary part, but that's okay. If the absolute value of the leading entropy is macroscopically large, that is deconfinement. Okay? But if you include the effect of other distribution modes, then the edge point of this rho 1 is not 1/2, but it's a function of other variables. So if you plug in this tachyonic value, even if the rho integral seems to be tachyonic, you get an intermediate integrand, which depends non-trivially on other variables. And this looks macroscopic in its real part, but it also has a fast phase oscillation. So that even though it looks tachyonic, after you do integral, there could be smearing effect due to this fast phase oscillation, essentially caused by complex fugacity. So this smearing, they suggested, is delaying the Hawking-Page transition, the deconfinement phase transition, even if you have entered the naive tachyonic region. Okay? So they have shown in a kind of better truncated model, it's a kind of gross-Witten-Wadia truncated model of the index, because the true index is so difficult to compute. They have identified the true deconfinement line of this better truncated model, and they have shown that the tachyonic line is this, and the deconfinement line of this this better truncated model is the edge of this gray line. It's substantially delayed, going very, very close to the Hawking-Page transition line, which is something like this. So compared to my naive one-dimensional model, in their better truncation model, where you integrate over more modes, Hawking-Page transition is more delayed. And this is a physical delay. It's not a fake delay due to the smearing or something. If there's a destructive interference here, this should be a physical one. And it's getting towards the Hawking-Page transition line, so it's a very promising one. Actually, they have considered a better improvement of this gross-Witten-Wadia model by including more realistic terms, and they have found that it's even more delayed, getting very, very close to Hawking-Page transition. So I think that delayed deconfinement picture is very, very convincing and natural. So probably this delayed deconfinement line, well, eventually we'll agree with the known black hole Hawking temperature line if all infinite corrections are made towards the true entropy. So I think this is one of the most exciting recent discoveries, this paper. Okay? I'm trying my best to understand things better. So 25 minutes over. So since I ran out of time, let me just finish by showing my conclusion slides and maybe some future directions and so on. Thank you very much, and sorry for the delay.
Thank you very much for the nice talk, Professor Kim. It was a really pedagogical one. So maybe we can unmute our microphone and clap up to show our appreciation. Yeah, now it's time for questions. So if you have question, please unmute yourself and ask your question. So I have already raised hand.
Yes, so may I ask one question? I'm Takeru Azumai, and thank you for your talk. I'm curious about whether your approach gives us some insight into the confinement, deconfinement phase transition.
I mean, which one gives? It's basically this. I mean, what they did.
So you work on the.
Yeah, the complicated thing is that, you know, Shiraz and company in 2003 have done similar deconfinement calculation for ordinary bosonic partition function, no index, at weak coupling. And of course, they attempt to get some qualitative pictures and so on. But at that point, everything is real. So there's no certainty having to do with oscillating phase and so on. So tachyonic direction was basically tachyonic point was deconfinement point.
Yes.
But I mean, the threshold of tachyonic point is the deconfinement transition point. I mean, the mismatch between tachyonic point and the deconfinement point is caused by this complex fugacity, which I think is another certain role played by fugacity. Yeah, which I really realized.
So especially the order of the confinement, the order of the confined phase transition is an interesting question, and so I wonder whether we can predict whether this is first order or second order or third.
I think it was first order. I mean, you know, it's competition of two distinctly separated saddle points, graviton saddle and the black hole saddle. It's first order. You know, in Shiraz's model, what do you call it? It's marginally first order, weakly first order, or something. It's something like borderline, right? So it's something like you draw an energy temperature plot. What do you expect for the black hole? What you expect for a black hole is something like this. This is the graviton line. This is the large black hole line. And this suddenly makes first order phase transition, absorbing great amount of latent heat. But Shiraz's weakly coupled model was something like this, right? Something degenerate. But you know, index has to be just quantitative. So it just predicts first order transition. I mean, at least in this model.
Yes. Thank you very much.
Yeah. Not predict, reproduce. Yeah.
Seok, question, please. suppose we were looking at a model with just one chemical potential. So we turn on only one of the n equals 4 chemical potentials. Now, in this approach that you described right at the end, that chemical potential could be an arbitrary complex number.
Yes. But you'd better choose it to be a carefully tuned one to minimize the smearing. And that's basically Legendre transformation.
I think that's what I was going to ask. I mean, if you Legendre transform, you'll just as a function of chemical potential, there's a complex plane. But when you Legendre transform with respect to charge, you get some curve on this complex plane.
Yes, yes. It is this curve, dotted curve, and this is the line where actual black holes are sitting.
Right.
And I think this is the I think this is the choice which shows cleverly I think this is the line which maximally obstructs the smearing during the summation.
I was wondering whether there was some interesting physics to be got from the partition function away from this line, just as a function of a general complex number.
Away from this line.
To start with, to start with, in gravity, you expect saddle points only on this line. Is this right? Or you can look at gravity with complex chemical potential and.
I think if you work with, I don't know, if you just work with Euclidean quantum gravity solutions.
Yes.
Maybe you can do more, but the solutions that are connected to the Lorentzian solution, I think should be sitting precisely on this line, I think. Because, these are solutions with fixed real charge, right?
Good. So you said that you will always get a saddle point of Euclidean quantum gravity, but then you try to continue to Lorentzian space and demand that it's good in some way, that it's a real solution or something like that, and that will pick out this line. Is it right?
I think so, but I feel that I should have always better understood this Euclidean solution business of Dario Martelli and Samir, which I didn't really. Do you remember what are the nature of the most general complex solution they studied in Euclidean?
I don't know it well, but my impression was that they were looking at some point in that paper they were looking at
I think
bunch of solutions.
I thought away from this line because they computed this vective action for independent chemical potentials and computed this even before Legendre transforming.
Yes. So
I think they generalized away from this curve.
And the special thing about this curve is that it admits a good Lorentzian continuation. Is this right?
Yeah, I think so. Yeah.
Okay, thank you.
I think so, although I haven't checked from the viewpoint of continuing Euclidean solutions. I think so, yeah.
Sorry, one more question, if you don't mind, Seok.
Yes, sure.
The remarkable thing here is that the index gets the black hole entropy, completely right? That at the level of the integers, your omega j's, there are no cancellations, though there could have been. Now, is the same true for the multigravitons? If one looks just at the index for the multigravitons.
Oh, you mean for the black holes, even if it's an index, the macroscopic leading entropies we produce, but you're not sure whether it's for gravitons, right? I think it's not. We know the growth of the graviton free energy, right?
Yes.
Not indexed. It grows much more violently than the index, right?
E to the power 5/6.
Yeah. The power is different. So I was wanting to ask to anybody because, macroscopic index agreeing with macroscopic entropy at the real order, I feel that usually there's a hand-waving argument, right? Index is bosonic minus fermionic, but if they are both macroscopic, like 10 to the 100 times 3 minus 10 to the 100 times, these are substantially different, but the difference is at the same order, right? If you take log, everything is indistinguishable, right, at leading order.
Right, but you could have applied this argument to the gravitons at very large energy.
That's right. That's why I'm confused, because if things are completely cancelled or almost cancelled, there should be always a symmetry reason or approximate symmetry reason or something.
Yeah,
so I was going
to ask you, why does it work so well for the black holes when it doesn't work for the gravitons?
I think this has to be answered by studying what magical structure exists for the graviton index, because whenever the index magically cancels, almost cancels, there are some symmetry reasons or so on. For toroidally compactified black holes, naive index is 0, so inverted U index or so on. And I remember it has to do with some hidden U1 symmetry.
But naively, actually, my intuition would have run the other way. That because you're computing omega boson minus omega fermion, yes. And they're both giving you roughly e to the s, right? And you're computing s at points which are separated by an order 1 amount. Yeah. And so you don't actually expect to get these these big prefactors, these 3 and 2. So in fact, I mean, we had some argument which I guess is clearly wrong, but we in our paper about why actually we expected the index to suffer these cancellations, except in special cases like 2 dimensions where you're basically the index just becomes the partition function. So somehow my intuition would have run the other way. Oh, maybe the last question about the gravitons is relevant, like why it doesn't work.
So is your statement of severe cancellation in the free quantum field theory picture?
Yeah, it's roughly some assumption that about how the degeneracy behaves between fermionic and bosonic. It's the assumption that if you take the scaling dimension and divide it by n squared, that the degeneracy is somehow a continuous function of that variable. I think if you make this kind of an assumption, then I think you would end up with the argument we had in the paper, which was that there's some suppression.
Yeah. Yeah.
I mean, it's a crude argument, but I guess this is just this question of whether intuitively you would expect the index to work or not. But I mean, I thought what happened in the graviton case was generic, that you had different dimension growth for the partition function and different dimension for the index.
But by the way, Subrat, I think that we were a bit misled even there. So the graviton growth, we found some, I think, square root behavior. Yes. I think if you take into account this phase cancellations, it's higher than e to the power 1/2, but lower than e to the power 5/6. Is this right, Seok?
I'm not sure. Phase cancellation is what?
There are some phase cancellations even in the graviton index.
So, but it won't push it all the way to the partition function, you're saying?
It does not. I'm saying that even there, though, we could have noticed that there was some cancellation, and you do better than what we naively see.
Right.
But it's not good enough to get the whole partition function, I believe. So it does better. The phase cancellation bumps you up, but not all the way. But for the black hole, it bumps you up all the way. It's incredible. I don't understand why. Okay, end of my question. Thank you.
I might have to do with the fact that graviton spectrum has some special property. It's not typical BPS operators, right? It's very, very special ones. In a sense, descendants of the simple half BPS ones and so on.
Yeah, multi-tracing of half BPS.
Yeah. So maybe due to this, some enhanced symmetry structure in a way, I mean, more cancellations are rendered. I mean, basically, if there are more hidden symmetries, more accidental cancellations can happen, right? Violating naturalness.
Can I say so? The argument is that if it's like you're summing -1 to the f, and you're summing it over an entire range of states which have the same, which contribute the same way to the index, right? So it's like it's not it's like summing an alternating series of positive and negative numbers. So it's like saying you're summing. So let's say you have some function s of d, which is where d is a dimension, and you're roughly summing it with -1 to the power d. And so that is what you would have thought would give you the cancellation, But I mean, it's clearly not correct, but because you're getting the degeneracy. But that the argument was, if you take some function like e to the s of d, just some generic function, and make it continuous as a function of d, and then sum it with -1 to the power d at large d, the sum will look very different from precisely because you'll get these cancellations between alternating terms. So it must be that what's happening for the black hole is somehow different. I mean, I don't know, but
Sorry, Seok, I have actually one more question, if you don't mind, after you finish.
No, not at all.
No, I don't have anything more to say. I'm just saying, yeah.
Okay,
Yeah.
great. Okay, so now that you guys control the index so well, we could ask the following question. What is the spectrum of supersymmetric states in n equals 4 Yang-mills as a function of energy? Okay, so up to energy is something order n, it's multi-gravitons, this we know. Okay, and from n squared
the true
onwards,
BPS spectrum. True BPS spectrum.
what? The true BPS spectrum, yes.
You mean this
At least
cohomology-like thing? Cohomology-like thing?
Not the true BPS spectrum. Whatever you get from the index, the log of the entropy of the index. Just a simpler question.
Something like, I mean, the dots that I plotted.
Exactly. Exactly.
Yeah, these things. Yeah.
So, so we know that now that n squared and above it's the black hole, and up to n it's multi-gravitons. This we know for sure, right?
You're asking when the new type of operator happens.
Yeah, but there's now a room between n and n squared.
Yeah.
Where something interesting presumably needs to happen.
Yeah, that's the small black holes, right?
Small black holes, but you know, once it becomes number times n square, that number, I mean, small black holes are number times n square with the numbers order 1.
Yeah.
It does not scale with n.
Yeah.
Room between that and n and number times n square. I mean, something like giant gravitons or something should play that role.
Yeah. So if you take this, I mean, I don't really precisely remember the threshold, but until certain order, graviton result is perfect. And slightly beyond that, I mean, the spectrum decreases compared to the naive graviton result. So that's this string exclusion principle of giant gravitons. So slightly above the graviton threshold, you can understand the decrease of the spectrum from the trace relation of this finite gauge group.
Yes.
And actually, until certain order, well, it's hard for SU5, so my student tried very hard with SU2 because there's an analog dotted plot for SU2, and for a little while pure graviton is right. For a little while you can formally explain it as graviton-like operators with trace relations, but eventually the spectrum grows. So I thought even for SU2 I would be able to find new operators. My student just repeated till j to the 11, 12, blah, blah, blah. I think 13 or 12, he did it. But still he didn't find any operators due to careful trace relations. SU2 to this charge, large charge order, all the index can be explained by graviton type operators subject to trace relation. Very high order, SU2.
There is a similar story that happens in EDS3, of course, right? Where there is this Debord story which says that you take gravitons and you just multi-particle them.
Yeah.
And the index agrees to much higher order than you would have expected. I mean, it agrees all the way up to Q1, Q5 by 4. Whereas you might have thought that something comes in at Q5. But it doesn't. And actually, there's some understanding of that there, because there at least the understanding is if you look for classical solutions. Classical giant graviton solutions, they don't exist except at a very special point in moduli space. So if you move a little bit off, some very special points in moduli space, then at least classically you can explain why these supersymmetric solutions don't exist. But I think the same is not true.
So this solution is not captured by index, you're saying, because it's moduli independent.
I think the solution. I think there is some understanding of why in ADS3 the multi-particling gravitons work so well. Whereas I don't think there is a similar understanding in ADS.
But it can't be that there are no additional states, right? Yeah, because the gravitons grow like e to some power that's less than 1, and then you set E like the entropy in the gravitons grows like e to some power that's less than 1, and then you set E is equal to n squared. That gives you n squared to a power less than 1, which is smaller than the entropy of the black holes.
Yeah, if you just plot the naive graviton index, sorry.
There has to be more states.
It becomes something like this. The graviton index is something like this. So here, it should be there should be huge more operators than predicted by graviton index. Yes. And even before imposing trace relations. Yeah. And I don't know whether imposing trace relation will make it lower or higher, because fermionic trace relation can increase something.
No, but you just look at the whole graviton partition function.
Oh, then it grows very fast, I think.
No, it grows like e to the power 5 by 6. So the entropy goes like e to the power 5 by, it's just like a gas of like a 6-dimensional gas.
Yeah. So as a function of charge, it grows fast, right?
Like let's say the charge is E. So it goes like e to the power 5 by 6.
E to the charge.
It's basically
e to the charge 5 by 6. Yes.
Yes. Now set,
and there's no scaling in n, of course.
Now set E equals n squared. That's n squared to the power 5 by 6, which is smaller than n squared. So it tells you that you take all the gravitons and just take those states at energy n squared. There's not enough to make up the states of a black hole.
Right. Yeah.
So there has to be something new.
Yeah. Of course. Yeah.
And I was wondering, whether one could. Yeah, I think that it seems to me that there's an interesting question of trying to identify what the saddle point is at intermediate energies. It seems to me that this new physics, and you guys have such good understanding of the index, you might just be able to find it.
Yeah.
Okay, so end of my question. Yeah.
Thank you. I think about it. Thank you very much.
Thank you.
So there is a raised hand by Professor Francesco Benini. So, Professor Benini, please go ahead.
Hi, it's Francesco. Hi. Good to see you. Good to see you. I have a question about the deconfinement transition and the relation with the delayed deconfinement.
Oh, yeah.
Can you go to that slide for a second?
This one, maybe.
Yes. So, okay, so here, so you are doing this manipulation on the integral formula. You have the Fourier coefficients, and essentially for instance, in this simplified model, you look just at the first term, and you ask whether the real part of f of x is positive or negative.
You mean by this simplified model?
Yes.
Yeah.
Now, and okay, so you compare this with the curve of the Hawking-Page transition that you have from gravity, if I understand correctly.
Yes. It's just black and blue.
Yeah. So now suppose that, okay, with some technique, okay, I do some saddle point approximation. I'm able to do some saddle point approximation, and suppose that for some reason I only get 2 saddle points from the matrix model. So I get the saddle point that, sorry?
2 being what? Black hole and graviton or what?
Well, yeah, so one saddle point is the one that Shiraz found.
Oh, the real one.
Yes, so, okay, one saddle point will be just the distribution of eigenvalues on the real line.
That's the graviton saddle point, yes.
And the other one is a saddle point that gives you this function of Zaffaroni, Hosseini, and Christoph, which is essentially, but the full analytic continuation, so the free energy, the analytic continuation of the free energy of the black hole.
Yeah.
So now I have these 2 saddle points, and suppose that now I do the naive thing that I just compare the real part of the 2 free energies. So for the distributed saddle point will be order 1, and for the other one, well, it depends whether the real part is positive or negative.
Yes.
So would that exactly reproduce the Hawking-Page transition from gravity, or not?
Oh yeah. That's Hawking-Page. Yeah, it is. Let's see. Yeah. I mean, when I drew this blue line, I did it in the way that you just said.
Okay.
I mean, this blue line is computed by that method.
Okay, so in a sense, if I understand correctly, the problem is here, and what delayed confinement is trying to answer, is that so one would like to see that actually there are no other saddle points. Is this the?
Well, at least no other saddle point which affects this Hawking-Page transition structure. If the delay happens until here, yeah.
I see.
Yeah, actually, the issue is about whether the saddle point that leads to the entropy function, whether it's the most dominant, it could be a local saddle point, but whether it's a dominant one or not is a damn difficult question, right? So since these people couldn't answer it in the full matrix model for the index, they consider this truncated matrix model. That's the reason why they truncate, because finding the most dominant saddle is so challenging for the full Yang-Mills index.
Oh, so when you talk about dominant, do you mean just looking at the real part of the?
Yes. The largest of all possible saddle points, or something like that. Yeah. I mean, all possible hypothetical, you know, not assuming anything.
I see. Yeah, I'm asking this because somehow it looks like either in the Bethe-Ansatz approach or in the approach of Murthy and so on, which is more saddle point, it looks like there is an opposite problem. It looks like you find a lot of saddle points.
Oh, yeah, but the subdominant one maybe?
All these,
non-basic
exactly. So you get a lot of what seems to be saddle points.
Yeah.
Which, I don't know, seems to ruin this picture because it looks like you would have transition well before.
Well, but they're subdominant, right?
No, I think that the point is that if they exist, so maybe they do not exist. If they existed, they would be dominant before the Hawking-Payne transition.
I see. So you suppose that they exist as a saddle point and compare the grand canonical free energy. That's what you say.
Yeah.
Sorry. So I actually investigated your subdominant saddle points, but I computed the entropy. So you know, these beta roots are labeled by K and R, right? Yeah. These more generalized beta roots.
Yes.
Yeah. For non-basic roots, for various values, I think we checked that your entropy divided by K, I mean, many people check that, right? This will be the microcanonical entropy for this beta root, so subdominant. But that doesn't mean that in grand canonical ensemble, it's still subdominant. And you say it's dominant, right?
Oh, I was talking about the index. So I was talking about the grand canonical ensemble.
Yeah. So you're saying if we assume that other betas are saddles, they could be more dominant, right?
Yeah, some region below the Hawking-Payne transition, I think.
I didn't know that. Oh, thank you. Oh. Do you have any feeling about that? No.
No. This is why I'm asking because in a sense it looks like one would be happy if there are just two saddle points, the AdS one and the black hole one, and then okay, in a sense you reproduce the result from gravity, but it looks like from these two approaches you get much more. So I don't know, maybe it should go away, maybe because some left-shift steam ball, or it's not clear to me.
But let's think about this TOE exam. It's very hard to construct new black hole solutions, but let's suppose this one. So, if you have AdS, it's a gravitational exponential potential, trapping potential. And if you take a very small black hole, it will be very, very small compared to the AdS radius. But for instance, if you take a point particle, you can boost it to rotate around certain radius, right? Point particle has this kind of geodesic, right? Couldn't we have this kind of small black holes? Although it will be terribly difficult to construct. Small black holes just rotating around the AdS potential due to centrifugal force. And if this kind of solution exists, can't we just put another small black hole just rotating around a different radius so that, sort of they're weakly interacting, there should be rotating multi-centered black hole. Couldn't that kind of solution just exist? At least when black hole sizes are small enough compared to the AdS radius. Because multiple point particles can just exist, rotating around each other, far from them. So something like multi-center solutions. Trapped in AdS, just rotating around. I mean, it would be terribly difficult to construct such supersymmetric multi-center blah blah. But I mean, this sloppy kind of argument just leads me to thinking that tons of more interesting black holes should exist. I mean, probably they might be subdominant in entropic sense, but I don't know.
Okay.
I was always wondering whether your non-basic beta roots could be corresponding to this, rotating multi-black holes or something. But,
yeah, no, it's a great question. Yeah, it would be
yeah.
nice to figure that out. Thanks.
Thank you very much. Thank you very much.
Seok, one more question, if you don't mind.
Yes, yes.
The index gives you a supersymmetric spectrum as a function of 4 charges.
Yes.
Do you expect supersymmetric Yang-Mills theory to have some special curve in the space of 4 charges? Or do you expect that there are interesting supersymmetric states, macroscopic number of supersymmetric states?
You're asking about the charge relation about known black holes, right?
What? Sorry?
You're asking about the charge relation of known black holes. Of
known black holes, or yeah, right. Presumably related to the fact that the index is also 4 parameters. Yes. Are you taking this to indicate that there's a special relationship of charges in n equals 4 Yang-Mills? Or do you expect there to be, I mean, is there a bigger question than the index for the number of supersymmetric states as a function of 5 charges that still remains to be found?
Can I try to answer by an analogy, which, can I try to answer by an analogy of asymptotically flat black holes?
Sure.
So if you consider BPS asymptotically flat black holes of 4-dimensional n equal to supergravity, asymptotically flat on in-bit black holes here, single-centered black holes can carry charge, but it cannot rotate. I mean, BPS black holes single-centered cannot have non-trivial angular momentum. So for single-centered black holes, J being 0 is the analog of the charge relation of, if it say, of, I think, analog of the charge relation of AdS black holes. And I think this charge relation appears from gravity side exactly due to the same reason. You demand a black hole solution with certain nice near horizon property and demand that killing spinors are well behaved. This leads to this condition. And in AdS, the near horizon property demanding gives rise to the charge relation. So geometrically speaking, this charge relation has same origin as the AdS5 charge relation. Now, here we know in asymptotically flat case, there are solution generating techniques. We know of much more complicated solutions. There are multi-centered black holes, right? Diodes and so on. So this electric particle, magnetic particle, they can be bound to each other. And since they are bound to each other, they have non-zero angular momentum. So this charge relation is violated by multi-centered black hole. But I wonder if there are an alternative charge relation here. I've never carefully seen. So one possibility, which I'm not sure is true or not, is that depending on which family of black hole you study, they might have their separate charge relations. But the concrete form of the charge relation might be different. In one branch, it might be J equal to 0. In a different branch, I don't know. There might be some different charge relations so that you just still have 4 independent charges out of 5. Well, would that be some scenarios?
But if that was correct, it would suggest that if I chose a random set of 5 charges, delta 1, delta 2, delta 3, J1, J2.
If that's the case, yeah, right. If that's the case, it's, yeah.
Then you would not have macroscopically many supersymmetric states for a random set of 5 charges.
If that's the case, you're right. I mean, there are special meanings of co-dimensional 1 slices, right?
Right.
But how about this? How about this?
Yes.
I mean, if you work with hairy BPS black holes, just allowing some dirty hair outside the event horizon, they violate charge relations slightly, right?
Yes.
And the geometric reason why this is allowed in the paper studied by Santos and Markiewicz, they have very ugly near horizon structures. At least they are mildly singular, I think.
Yes, they're singular. Yes.
Nice AdS2 or something.
Yes.
So accepting ugliness of the near horizon allows one more parameter, right?
Right.
So is it acceptable singularity when why bother?
Yeah, that sounds more plausible to me somehow. So what you're saying is that there is a bigger question. We want to find entropy as a function of 5 charges. And the index is telling us somehow, it divides it up into orbits and gives you maximums along those orbits. But there's a bigger question that would be nice to know the answer to. That is more information than in an index.
Yeah. I mean, along this possible new solution, can I ask your opinion about, again, a hypothetical solution that I have in mind? So basically, the hairy black hole solutions you considered, it's having single black holes with single event horizon, and you have some hair, some gravitons just condensing around here.
Yes.
And if you use some semi-classical description, it may be a quantized version of a point particle probe, which is just moving around the black holes.
Yes.
So at least if you stick to this graviton hair moving around the black hole, the charge carried about the hair is much, much smaller than the macroscopic one, right?
Sorry, the charge carried in the hair. No, the charge carried.
They can be macroscopic and scalar n square.
Yes, yes, I think so.
Oh, they can.
Yes.
Oh.
Well, I don't know about supersymmetric black holes, but non-supersymmetric black holes they could, right?
Okay. So they can carry actually substantial amount of one more independent charge. If that's possible.
Yeah, I think so.
Okay. But it's basically gravitons, right? I mean, how can their contribution be n square?
It's a Bose condensate of gravitons.
Bose condensation of graviton that.
You know, it's a more.
Oh yeah. I mean, anything that is realized by classical solution has natural overall n square.
That's right.
Oh, it's inverse Newton. Okay.
Yes.
Okay. Sorry. So yeah, if hairy black holes are serious candidate.
I think hairy black holes might be serious candidates. Right?
It's not just five. Then it's not just 5 parameter solutions, right? You can have lots of different hairs and.
But that's discrete. That's discrete numbers. I mean, hairy black hole solutions are also have as many parameters as there are charges. It's not like you can vary the amount of hair continuously. That's set by dynamics. So you would get, I think, just 5. My guess is 5 parameters.
Well, but in principle, there are infinitely many Kaluza-Klein modes coming from S5, right?
Right. So you could have infinitely many discrete things. And then
each slice is all 5 dimensional.
That's
all.
Right.
Oh yeah.
That's right.
I see. Thank you.
Okay, but thank you very much. Sorry for really having taken up so much of your time.
Thank you for new ideas. Thank you for new ideas, everybody. Yeah.
So is there any other questions? Yeah, it seems that there are no more questions. So thank you very much, Professor Kim, again. So it was a very nice talk, and I hope this is not too late for your dinner.
No, it's okay. No, it's okay. Completely fine. Thank you very much.
Thank you very much. Have a good night.
You too. Thank you very much, everybody. Yeah.